Welcome to my lecture about BJT for resistor biasing. What have we done so far? So far we have looked at single resistor biasing of a BJT, the simplified hybrid pi model of a BJT, and the small signal equivalent circuit of a common emitter amplifier. Let's look at the single resistor biasing in greater detail. Here we have the common emitter configuration using a single resistor to bias the BJT. The Q point is determined by the base current, the collector current, and the collector emitter voltage, and these three can be calculated according to those equations on the right hand side. Let's do a little example where VCC is 20 volts, RB 100 kilo ohms, RC 500 ohms, VBE on 0.7 volts, and beta 100. Please do those calculations and stop the video while doing so. The answers will be revealed in 5 seconds. Here we have it, the base current at 193 microamps, the collector current 19.3 milliamps, and the collector emitter voltage being 10.35 volts. This all looks good. However, beta is a device parameter and varies significantly. Here we see a little snippet from the datasheet of a 2N3904, and we see that beta can change between a minimum of 100 to typically 300, and the maximum is not even specified. This ratio of 3 to 1 is not uncommon at all, and of course this has consequences. If we do the exact same example, but this time let's change beta to 200, we get a very different Q point where the collector current is 38.6 milliamps, while the collector emitter voltage is 0.7 volts, which is of course very close to saturation. So again, let's compare this for a moment. Beta being 100, we get a collector emitter voltage of 10.35 volts. At beta 200, we get a collector emitter voltage of 0.7 volts. And we see that the Q points vary wildly with the device parameter. And at beta 200, the device is close to saturation already. Of course, this means that we need a different way of biasing, where the collector current and the collector emitter voltage are much less dependent on beta. Hence, the 4-resistor biasing scheme. Here we have it. The two resistors R1 and R2 essentially build a voltage divider, together with the BJT, a collector resistor, and an emitter resistor. How do we analyze this circuit? Well, we replace R1 and R2 with the Thevenin equivalent, and we calculate the remainder of the circuit according to the single resistor biasing scheme. So, again, let's look at R1 and R2, replace them with the Thevenin equivalent, which gives us a Thevenin equivalent voltage and a Thevenin equivalent resistance, where the Thevenin equivalent resistance is the parallel configuration of R1 and R2, and the Thevenin equivalent voltage is the voltage divider across R2. And then the remainder of the circuit can be calculated according to the single resistor biasing. That uses the exact same equations as before, but we now have the Thevenin equivalent voltage and a Thevenin equivalent resistance in those equations. Let's do a little example where we have these component values and device parameters, and please stop the video while you do the calculations. Here we see the result, the collector current being 5.3 milliamps and the collector emitter voltage being 14.2 volts. Let's do another example with the exact same component values, but let's change beta to 200, and again, stop the video while you do the calculations. The result is a collector current of 8.6 milliamps and a collector emitter voltage of 10.5 volts. So if we now compare those two, we see that while the Q point changes with the device parameter, it does not do that by much anymore. So the 4-resistor biasing results in a Q point which is much less dependent on the BJT device parameters. Okay, what are we going to do next? Let's look at the hybrid pi parameters and how do those change. Let's include the signal source. Let's include the load resistance. Let's look at the small signal equivalent circuit. Let's determine the input resistance, the output resistance, and finally the voltage gain. Thank you.